Hello everyone, welcome to force between two parallel conductors. Now let's say we have two parallel conductors like this separated by a distance r. Now when a current flows, it produces a magnetic field around it and it experiences some Lorentz force. And here these two conductors, they will be in the magnetic field of each other's magnetic field, and they will experience some force between them. So now there will be two cases when the currents are in the same direction and the reverse direction. So now let's take it when current is in the same direction. Now let's find the magnetic field at point P in this conductor due to this current I1. So here, using right hand rule, we can see that the fingers curl towards point P. That means that the magnetic field is inwards. And here B1 will be equals to mu naught I1 by 2 pi r. And here this conductor will experience some Lorentz force due to this current and this magnetic field, which is F2 is equals to B1 I2 L sine theta. But here theta is just the direction of current cross and vector multiplied by the magnetic field's direction. So here the current is going like this and the magnetic field is going like this. So here, as you can see, they are perpendicular. That means sine theta will be 1. So here we will have the equal length in both sides. So we can just divide it by length to make it easier for us. B1I2. And here we can write it as force per unit length, or simply F2, which will represents the force F2 per unit length, which is equals to mu naught I1 I2 by 2 pi r. Now here again we can find the direction of F2, which is given by Fleming's left hand rule. So here let's find first the magnetic field, which is going inward and the current is going upward. That means that the Lorentz force goes like this, right? Father, mother, child, magnetic field, direction of current, and here the Lorentz force, which should go like this actually, but the direction is reversed in an electron for an electron. So the Lorentz force is going towards the conductor C1. Now here, for simplicity, we can just use similarly F1 will be equals to mu naught. That will be too far. You will have to show some derivations. Similarly, F1 will be equals to B2 I1L. And here you can also draw a magnetic field like this, like that. Point Q, and here due to this current I2 at a point Q on conductor C1, here it will be outwards, it's coming outwards, right? So that is B2, it is outwards, and here F1, which is mu naught I1 I2 by 2 pi r, because here the B2 is equals to mu naught I2 by 2 pi r, and here its direction, I'll just tell you, it will be inwards, F1, Fleming's left hand rule again. And here you can see that F1 and F2 have the same magnitude, and they are in the same direction. They are acting towards each other. That means this is attractive force. So you can see that the force experienced between two parallel conductors when they pass current in the same direction is an attractive force. Now this second case is almost, you have to change only the crucial and critical words. So in opposite direction, the derivation is actually the same. So you don't have to change anything in the derivation, but in the figure you'll have to change. So first, let's say that this current goes downwards, and and you'll have to rub some of these out. Now, this for the first I1 part, it's actually the same, so I didn't have to rub it out. You know, this goes inward. No, it's not the same actually, because here, now the direction of this F2 is now this, right? Sorry, Fleming's left hand rule. So here, the magnetic field goes there, and the current goes down. And here, the Lorentz force should go here, but it goes here, or let's say the force per unit length. So that means this experiences outside. And similarly for F1, first let's find that this and this is also inward. The magnetic field due to conductor C2 at point Q is well going inwards. So this is also inwards. And here the force per unit length experienced by it is well, magnetic field is inwards, current is upwards, and the Lorentz force would go like this, but in electron it's reversed, so it goes outside F1. As you can see that F1 and F2 have the same magnitude again, because the derivation of its magnitude is same, but it is acting away from each other. That means that the force is repulsive. And from this force per unit length, you can find the definition of 1 ampere. So users have to put R is equals to 1 meter, these two as 1 ampere, and you'll get F1 is equals to mu naught into 2 pi, which is 2 pi into 10 power minus 7 Newton per meter. Now, well, the definition comes from here. 1 ampere of current is said, or a current is said to be 1 ampere when when the force per unit length between two parallel conductors in a vacuum separated by 1 meter experiences a force of 2 pi into 10 power minus 7 Newton per meter, right? So that is the definition of 1 ampere. Simple, and if you learn something new, please like and subscribe. Thank you.